Today we're going to talk about continuity and the intermediate value theorem. So continuity we dealt with again in pre-calculus. So a function is continuous if three conditions are met. So the three conditions for continuity: first, that there is a function value there. If there's a hole or an asymptote, then the function is not continuous. Second, the limit has to exist. So it has to go to the same location on both sides. And the third condition is that whatever the function value is, the limit value is the same exact thing. All right, so we're going to use the graph to fill out this table. So we're going to look at a variety of different values, and we're going to look at what the output is, the limit from the negative side, limit from the positive side, the limit, that should just say A, and then is it continuous? Okay, so as we go to -3, the function value there is about 1/2, it looks like. The limit from the negative side is going to be -2. The limit from the positive side is 1/2. If the limit from the left and the right are not the same, the limit does not exist, and which makes this not continuous because the limit doesn't exist. At -2, the function value is 3. The limit from the negative side is 3. The limit from the positive side is 3, which means the limit is 3. So since the limit exists and is equal to the function value, it is continuous. Okay, at -1, there is no function value. There's a hole in our graph. The limit from the left is 1. The limit from the right is 1, which means the limit exists. But since there's no function value, this is not continuous. Okay, -1/2 right here. The function value is that little dot, so that's going to be 1/2. The limit from the left is going to 1. The limit from the right is going to -1, which means those are not the same, so there is no limit. So this is very much discontinuous. Okay, at 0, and this is a little bit tough to see, this is not a hole, that's just the origin on the graph. So at 0, the function values maybe -3/4 or so. The limit from the left and the right are both the -3/4, which means the limit exists and is -3/4, which means it is continuous. At 2, the function value appears to be 1. The limit from the left and the right are both 1. So the limit is 1, the function value is 1, which makes this continuous. And finally at 3, the function value is 3. The limit from the left is 2. The limit from the right is 2. So the limit exists and is 2. The function value exists and is 3. So they're not the same, which makes this discontinuous. So on a graph, it's really easy to see if there's any sort of a jump, a hole, anything like that, the function is discontinuous. But if it's just goes through the point, just normal, then it's continuous. Okay, so we're going to draw a function that is not continuous at 2 that shows different types of discontinuity. So a point of discontinuity can look like this, where you have a hole on the graph. Jump discontinuity it jumps like that. Infinite discontinuity means there's going to be an asymptote. Okay, an oscillating discontinuity is something where the graph, and this is kind of hard to see, the graph just doesn't approach a single value. It just keeps da 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 da. And this kind of, I didn't draw it great, but it's something where it just oscillates to no particular value. Okay, so we're going to sketch a graph with the indicated features, a negative value of f of 5 and a positive limit as x approaches 5. So there's 5. So if it has a negative function value, just put a dot down here, and a positive limit, could look something like that. Second one, f of negative 3 is 2, but there is no limit as x approaches negative 3, and there's no vertical asymptote there. So f of 3 is 2, but there's no limit. So I'm just going to do something like that. So there's no limit, but there is a function value. Okay, so we're going to determine whether the function is continuous. So first condition is does f, and the only place this is going to be discontinuous is at 1. So f of 1 exists and is 3. So then we want to look at the limit as we approach 1. So as we approach 1, we're looking at this guy here. Well, for this limit, we need to factor. So I'm going to factor out a 3, which would leave me with x squared minus 1. So then I have an x minus 1 on the top and an x minus 1 on the bottom. So then this limit is the limit as x goes to 1 of 3 times x plus 1, which is going to be 3 times 1 plus 1, which would be 6. So it has a function value and it has a limit value, but they are not equal. So f of 1 does not equal the limit as x approaches 1. So this is not continuous. Okay, we're going to find a value of k that makes this continuous. So again, the issue is going to occur at 2. So we want to find a value so that at 2, these go to the same place. So I want to look at where, as x approaches 2, of the 2x minus 3, where is that going? So we're going to have 2 times 2 minus 3. So 4 minus 3 is 1. So I need this to also go to 1 when x goes to 2. So I'm going to set it equal to 1 and essentially solve this equation. So k times 2 squared needs to equal 1. So k times 4 equals 1. So k is going to be 1/4. And that will make it continuous because it's both going to go to 1 if k is equal to 1/4. Next, we're going to graph the piecewise. So when x is less than 2, we have the line negative, or 2x minus 3. So start at 3, go up there. So this part is a line, and then past it is going to be a parabola. So we know we plug in, if we plug in 1, so we're looking at 1/4 x squared. If we plug in 2, we're getting 1. If I plug in 3, that would be 9/4. So a little bit over 2, and it's just going to continue up as a parabola. So here we have a piecewise function with some unknowns, a and b. So first it says find all choices of a and b so that it would be continuous at 1. which means we want the limit as x goes to 1 of ax to equal the limit as x goes to 1 of bx squared plus x plus 1. So we'll evaluate at 1. So this would be a times 1. This side would be b times 1 squared plus 1 plus 1. So a equals b plus 2. So any value where a minus b is equal to 2 will make this continuous. Next, we're going to draw the graph when a equals 1 and b equals -1. So if we plug that in here, we'd have 1 minus a -1, which is 2. So we are going to have a continuous graph. So if a is 1, then my top function there is just going to be x when x is less than or equal to 1. And then if b is -1, we're going to have a negative x squared plus x plus 1 when x is greater than 1. So for this graph, when x is less than 1, we just have the line y equals x. So we're just going to have that line there. When x is greater than 1, so it's going to be 1 when we have a plug in 1. If we plugged in 2, we'd have a -4 plus 2 plus 1, so we'd again be at 1, and then it's going to decrease from there. And you can plug in more values if you need to, but it's going to look something like that. Suppose f is continuous and the limit as x approaches a of f of x is L, find f of a. Well, pretty straightforward. F of a would have to equal L, and the justification, I would just say definition of continuity. If the limit as x approaches a of f of x is equal to L, draw a graph to show why each of the following statements may fail. So we're saying the limit is L, but that doesn't necessarily follow the second statement. So f is defined at a. Well, I can have a limit at L, but there doesn't necessarily have to be a limit or a function value in order for there to be a limit. F of a equals L. So the limit is still going to be L, but I can have a function value that's different. And lastly, f is continuous at a. And both of those previous graphs would be the same thing. I can have it where there's a limit value and it's not continuous. So the intermediate value theorem is a fairly obvious thing, but it's an important thing. Okay, so it says that if there's a function, if the function is continuous on the closed interval, which means it has to be continuous including a and b, you can't have a jump or anything. So if it's continuous on a and b, and f of a does not equal f of b, if n is a number between f of a and f of b, then there's at least one number c on the open interval ab for which f of c is equal to n. So here's an illustration of that. Here's a, here's f of a, here's b, there's f of b. Okay, so if n is some number in between f of a and f of b, then there is some number in between a and b, we're calling c, where f of c is equal to that value. Because in order to draw a line from here to here, to making it continuous, it has to go past n. If n is in between these two values, then somewhere it's going to have to equal that. We don't necessarily know where it's going to equal that value, but the intermediate value theorem guarantees that if n is between f of a and f of b, then there's some value of c in between a and b where it's going to cross through there. It just has to. There's no way to get from here to there without passing n along the way. So if f of x is 2x cubed minus 4x squared minus 6, does f of x equal 0 somewhere in between 2 and 3? So what we're going to do is we're going to plug in 2 and plug in 3. So I plug in 2, we're going to get 2 times 2 cubed minus 4 times 2 squared minus 6, which is going to equal negative 6. If we plug in 3, okay, if you plug that into your calculator, you're going to get 12. So, if f of 2 is negative 6 and f of 3 is 12, does f of x equal 0 somewhere in between there? Absolutely. This is a continuous function. So if we're going to go from negative 6 to a 12, there's no way you can get from here to there without crossing 0. You must pass 0 to get from negative 6 to positive 12. So when you're taking the AP test, they will have questions like that. And they'll say, does f of x equal 0? And you can't just say, well, yeah, duh. You have to have a formal justification. So the formal justification is going to look like this. Since f of x is continuous and f of 2 equals negative 6 and f of 3 equals 12, by the IVT, this is the intermediate value theorem, there exists a c into 3 such that f of c is equal to 0. So you have to state the function values, you have to state the theorem that you're using, and then you can make your conclusion. Okay, graph to confirm. I'm just going to make this real straightforward. I'm going to say that's negative 6, that's 12, that's 2, that's 3. Okay, f of 2 is negative 6, f of 3 is 12. There's no way to get from there to there without crossing 0. Okay, does f of x equal negative 5 on the interval from 2 to 3? Well, is negative 5 in between negative 6 and 12? Yes. So yes, if it was outside of that range, then it's not necessarily true. In this case, this one's just going to be increasing, so yes. But f of x does equal negative 5 because negative 5 is in between negative 6 and 12. For the justification, we're going to take this same exact statement. The last thing is going to be different. So our justification, just like the last one, since f of x is continuous, you have to state that part. F of 2 equals negative 6, f of 3 equals 12. By the intermediate value theorem, there exists a c between 2 and 3 such that f of c equals negative 5. For D, does f of x equal 40? Maybe. But the intermediate value theorem does not guarantee that. Okay, so because 40 is not in between negative 6 and 12, we cannot use the intermediate value theorem to show that. Okay, so let's look at some actual AP questions. So f of x is continuous, and f of negative 3 is 2, f of 3 is negative 2. Which of the following must be true? AP loves those kinds of questions. So I'm going to draw a little picture here. So we have negative 3 and 3, 2, negative 2. Okay, so negative 3 is 2, and 3 is negative 2, and whatever. Okay, whatever happens in between, we don't know. It is a function, so it's not going to zigzag, but it is continuous. So must be true, f of 0 equals 0. That does not must be true. It has to equal 0 somewhere, but it doesn't have to occur at 0. F of 1 is 1/2. Does not have to be true. It has to hit 1/2 at some point. F of 2 is 20. Nope. F of c, and now look at these two last ones. F of c equals 1. So they haven't forced a specific thing to equal 1. And the intermediate value theorem says it has to pass through every number between 2 and -2. So it does equal 1 somewhere between -3 and 3. So it's E that is correct because C is the x value, not the y value. So that's that. So if g of x is sine of x, and it is continuous from from 7 pi over 6 to 3 pi over 2 by the intermediate value theorem, g of x must equal what value in this interval? So we're going to plug in. So we're going to look at what is the sine of 7 pi over 6. And it may be handy to have a unit circle available. So sine of 7 pi over 6 is -1/2. Sine of 3 pi over 2 down at the bottom of the unit circle is going to be -1. So we're looking for which value it is. The intermediate value theorem does apply because it's continuous. And if we look at these three values, okay, we're going from a -1/2 to a -1. So the only value that's between those is E. If it's going from -1/2 to -1, it has to pass through -7.77 or 0.77. Okay, so this next one is an actual AP problem from 2014. So train A runs back and forth on an east-west section of a railroad track. Train A's velocity is measured in meters per minute, is given by the differentiable function of V sub A of t, where t is measured in minutes. Select values of V sub A of t are given in the table above. So we have some time, so the different velocities, so at time 0, the velocity is 0, at time 2, the velocity is 100, at 5, the velocity is 40. A, the velocity is -120, which means it's going backwards, and 12 is at -150. It says, do the data in the table support the conclusion that train's A velocity is -100 meters per minute at some time between 5 and 8? Give a reason for your answer. So that's that justification. So for the intermediate value theorem to apply, it has to be continuous. This word in here you will learn much more about next week. But if the function is differentiable, that means it's continuous. So it doesn't say it's continuous, but it sort of does when it says it's differentiable. So if the function is differentiable, then the function is continuous. So the intermediate value applies. So if the function is differentiable, then the function is continuous by the intermediate value theorem. Since we're looking at -100, we're looking between 5 and 8. Okay, between 5 and 8, we went from 40 to -120. So since -120 is less than 100, and -100 is less than 40, there must be some value some t in 5, 8 such that V sub A of t is equal to -100. So you can say it like that, or just fill in the blanks. So since the f of x is continuous and f of 5 is 40 and f of 8 is -120, by the intermediate value theorem, there exists a number between 5 and 8 such that f of c is negative 100. So as long as you're saying it's continuous and you give the function values, then we're good. So last problem. The table above gives several measurements of the velocity of a particle moving along a straight line. What is the smallest possible number of times where v of t is exactly 4 meters per second if v of t is continuous? Okay, so we're looking at this table of values. Okay, and why don't we go ahead and just kind of graph it for ourselves. So looking at these numbers, there's 5, I'll go 1, 2, 3, 4, 5. And I know it doesn't, well, let's see. So at 0, we're at 3.35. So 1, 2, 3.35. Okay, at 5, let's say that's 5, we're at 4.25. At 7, we're at 2.75. At 9, we're at 2.55. And at 14, we're at 4.7. Okay, so this graph kind of goes like that. 4 is here. So we're at a number less than 4, we're at a number bigger than 4, we're at a number less than 4, less than 4, bigger than 4. So at a minimum, it has to go past 4 3 times. And that is the intermediate value theorem.